I have the pleasure of introducing Maria Antónia today. So Maria Antónia Carravilla is an associate professor and director of the doctoral program in industrial engineering and management at the University of Porto. She's also a senior researcher at INESC Tech. INESC, for those who don't know, is one of the most important scientific research and technological development institutes in Europe. Actually, it's one from which we at Optima can certainly get a lot of inspiration. Indeed, Maria Antónia's expertise is very much connected to what we do in Optima. She focuses on solving real-world problems in both industrial and public sectors. This includes manufacturing, logistic companies, higher education institutions, just to cite a few. In the process of solving these numerous applied problems, Maria Antónia has also made innovative theoretical contributions to the fields of mathematical programming and meteoristics. Maria Antónia is also a brilliant teacher and educator. She's a deep thinker on how we can better teach operations research, having received several teaching awards and presented keynote talks and organized streams on the topic of better teaching at some, or if not all, of the most prestigious OR conferences. I have had the pleasure to know Maria Antónia for about 15 years now, and she's among the kindest, smartest, and most pleasant people I have ever met. I actually share this opinion with many other colleagues around the world who have also benefited from her mentorship over many, many years. Maria Antónia, thank you for being ready this early in the morning. And it's a great joy that I ask you to speak to us.
So thank you very much. I think I shouldn't speak anything else because all that I can say will worsen your presentation. Thank you very much for your presentation, Alison. We really we work in sorry. I'm deeply grateful for being here and for having this opportunity to be here and to speak in an Optima seminar. And the theme that I would like to speak with you is about these cutting natural stone panels, and mainly about a problem that they have in the production, which is overcuts. We have this project with this natural stone cutting company, and they have a lot of challenges, of logistical challenges, besides this one that we are addressing in this presentation. So it will be, and I decided, I already told you that I decided to avoid, I will speak about the mathematical programming model, but I won't show anything about the model. So we will only discuss and see what is behind the model. So we have this company that has many that has those stones, and they have to be cut mainly for facades of buildings. So they have a lot of stones, and the stones have some defects on them that we don't know, and that they have different shapes because they are natural stones. And the challenge is to have, we have several stones, and we have several pieces that we must cut out of these stones. So we choose one stone, and this stone here will be with us during the whole presentation. It has this area, And the first thing that they do now in the company is stone by stone, they choose which pieces they will put here, and we will see how they did it. So they used 3 pieces of this first type and put them here, and then another piece of this type and put them here. Here we understand why they put the piece here and not here, because there is a defect. And the last piece, they put it here. So, and they don't, the piece is not, has a space between it and the other pieces. So our objective will be to build a model where we can minimize the resources used, and that are at the same time the raw materials, to cut all the pieces that we have to cut, minimizing the raw materials that are used, and minimizing the machine time. And we have to take care of special positioning constraints due to overcuts. And we will see now in the following some how it is cut and why we have these problems of overcuts. So it's the first cut has already been made, and now let's see what happens. So there is a lifter, a vacuum lifter, that is used to separate this big stone from the other. Okay. And this takes time. Okay. That's a decision that we can take, but it takes time. And then we have this piece that is has been separated, and we have the other pieces. So now that the pieces are separated, the machine can begin to cut everything. So we have this first cut here, and it's horizontal cuts that are made. This one, and then here, and then here. And you can see that the cuts, we have this overcut. So we only need to cut the piece until here, but due to the saw, we have an overcut. And here also, if we want to cut until here, we must cut a little bit more. So that's why the pieces here must be apart from each other. And then, finishing the cut, the machine must change, rotate 90 degrees, and it begins to cut in the vertical position. Okay. Everything will be cut. Okay. So all the vertical cuts are done. Here, 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 and here. And now we have all the pieces that have been cut. So they have some information on it. We have here the example of the piece that is the plate that has been cut, and now it goes away. And we have here from this area, this was the used area, and they took 4 minutes to position the pieces in the plate, and it took 6 minutes and 52 seconds to cut the plate. So we have this cutting time per piece. So we want to increase, our objective will be to increase the used area, or at least to, it's that we want, and also to reduce the cutting time. That's both objectives at the same time. So we want to cut pieces from slabs. The objective is to minimize the used resources that are the raw materials and the machine time. And we want to take care of special positioning constraints due to overcuts. So we have a normal cutting problem with 2D pieces, and but we have these overcuts that must be dealt with. So we decided to use a model that we call the floating cuts model. It has been published this year by us, and this floating cuts model allows us to guarantee the guillotine cut, and also, of course, that the pieces are separate from each other. So I'll go through this model just to show. We have this floating cuts model has, we proposed a 5 arcs model that is for first order non-guillotine cuts. It's this example. And we propose a 4 arcs model for guillotine cuts. That's this one. Okay, and the cuts in this case are those ones, and the cuts that interest us in this example are this in the lower part. So we will use this build model for guillotine cuts, and I will go through the model so that you can see what happens. We have an enumeration tree. If we cut the big piece in 4 smaller pieces, we have the top left, the top right, the bottom left, and the bottom right piece. And those pieces can also be cut in a top left, top right, bottom left, bottom right. Each one of them can be cut in these sub pieces. So and this is really a recursive structure. We could cut these pieces once again in 4 pieces, but we must, as it is really a parametric model, so we have to define beforehand this h that is the parameter. We have h equal to 1 is this big piece, and then if it is cut, we have h equal to 2, and here we have h equal to 3. So in our example, we use this h equal to 3, the maximum h that is possible. So, and we will use it as a parameter, so we can guarantee that we have the optimal solution for a value of h. Okay. So for h equal to 3 in the limits, we have this first cut in red, and then each one of the sub-rectangles is cut once again. Okay. And then what are the decisions of this problem? We have 3 alternative decisions. We can, for each sub-rectangle, we can decide 3 things. Or the sub-rectangle is cut, like this example here, and we must define how. So we must define the height and the width of each cut. An item of a certain type can be assigned to the subrectangle, or the subrectangle is not used. So we have a lot of pieces of each type, and we can decide what to do if we cut the subrectangle, if we assign an item to the subrectangle, or if we don't use it, we leave it without being used. And what are the constraints of the problem? First, the dimensions of the child subrectangles. So there is a relationship, of course, between the length of this rectangle and of this rectangle and the length of the subrectangle from which they were cut, and the same for the width. And also, we can't, of course, put a piece in a subrectangle if the piece doesn't fit inside the subrectangle. We have also demands of each items of each type, and we have some initialization constraints and some constraints that strengthen the model. So all those constraints, you can see them in the paper that I've shown you. So, and now we must address sometimes it works, sometimes it doesn't. So now we must address the overcuts. And we will see once again the panel that we have seen at the beginning. So for you to remember, it was this panel, this part was, we used the lifter to, they used the lifter to put it apart from here. And we have here the cuts with all the other overcuts. So how can we address the overcuts? We have here in this figure all the three ways to address the overcuts. We can, if we align all the items, we don't have problems with overcuts. So here is an example of these two items were aligned. So we can cut them and there is no problem with overcut. Okay. And they can be aligned, of course, vertically or horizontally. Another way to address the overcuts is to guarantee that the distance between, and here is an example, that the distance between the pieces is at least this delta, where this delta is the value of the overcut. And finally, we can predict or use the lifter to separate partially cut items. So these are the three ways to address overcuts. And but to address those overcuts and to be able to guarantee that the pieces are really aligned, that this delta is guaranteed, we must add something to the floating cuts model, because the floating cuts model only gives us the information of this certain piece is positioned in a certain subrectangle, but we don't have information on where it is positioned. Okay, so we must add add continuous placement variables to the floating cuts model to guarantee the overcut constraints, and in our case also placement constraints such as avoiding defects in the plates. So we need really a hybrid milk model to address it. So we will use the floating cuts model that has these decision variables. Is the sub-rectangle cut in smaller rectangles? Is an item assigned to the sub-rectangle? And isn't the sub-rectangle, the sub-rectangle is not used? And we add these new decisions. What is the lower left? What are the lower left coordinates of the sub-rectangles? And what are the lower left coordinates of an item of type I assigned to the sub-rectangle? And we have also these decisions to take. The items are aligned. The distance is between them is at least this delta, and these lifters, the lifters will be used or not. Those are the new decisions for the problem. Okay, so, and we have these new constraints. We have the constraints that relate these points with the positioning points of the items, and we have the constraints that guarantee that the items are aligned, or that, of course, we use for this binary variables. If the items are either aligned, or the distance between them is at least delta, or the lifter is activated. And the objective that we use is on one side to minimize the raw materials used, and on the other side to minimize the number of times the lifter is used. And this number of times the lifter is used is related with the time it takes to cut if we use the lifter. As we have seen, the lifter takes a lot of time takes a lot of cutting time. So, and we use this new model with and we have a first pattern. We obtained the first pattern that I will show you. So in this first pattern, what do we have? We have exactly the three examples. We have here in this first part, it must be cut, and then the lifter must take it apart, because otherwise these cuts can't be made, and these also can't be made due to overcuts. And besides that, we have this piece that is apart from the others by a delta equal to 10, so that it can be cut, and the other parts can also be cut without damaging the piece. So, and now we have a lot of next steps to do, and our next steps are we must include in the model the gripping size of the lifter, so the pieces that the parts of the big piece that we lift using the lifter must be bigger than the gripping size. And we have other operational constraints that we must deal with. we have mainly the pieces that they cut are from a certain number of types, and there are many pieces of each type used for the facades. We must deal with this problem. We didn't yet solve this problem. If we have many items, instead of assigning only one item to each sub-rectangle, we could assign groups of items, either vertically organized or horizontally organized. And we must handle defects that we don't do it yet. So this is our problem, and the point where we are yet. We think that we will have to, besides the model, we will of course have to resort to some heuristics, I don't know, to solve the problem, because the problems are huge. They have a lot of big plates to cut for a certain facade, and we must deal with it and solve the problems, because that's our goal, the final goal for the company. So this is the presentation. We have here an example of a big plate where the pieces are not here anymore. The pieces that have been cut are not here anymore, and we have here the overcuts. So thank you very much for your attention, and I'm open to questions, of course.